The title, Chapter 6, Responses and Adaptations to Aerobic Endurance Training. I'm going to try my best not to read out I'm going to try my best not to directly read off the slides, but these are the objectives. I want to make sure you guys know what happens during aerobic exercise, and I want you guys to know what happens over time. So that's acute and chronic. I want you to understand the factors that influence these adaptations. I want you to understand and identify the factors associated with overtraining. And that, I don't think we'll get to that today because it's a 50-minute class. You'll actually pick that up with Dr. Gaines. And then you will eventually identify the physiological consequences of detraining. So I think the objectives already like defined acute and chronic adaptations. Like I said before, acute responses happen in real time. Chronic adaptations happen over a long period of time. It's not like the adaptations that occur between minute 1 and minute 50 of exercise. These are the adaptations that occur between exercise experience 1 versus exercise experience 200. And so these effects are also regulated by intensity, duration, and frequency of physical activity. I think a good example of this is if you are one of those people who goes for like an hour-long run at a very slow pace, you're going to get better at that, but you're not necessarily going to get better at speed training. You're going to get better, or you're going to experience the appropriate adaptations to what you were doing in the first place. And I'll explain that more a little bit later. So, are any of you guys runners? Okay, you run. So, the first day you ever ran, like how did that feel? Did you feel great or yeah? Yes. Hmm. Okay. And so, like you said, what's your name? Luke. Like Luke was saying, the first time you do something or the first time you run, it is not fun. It's probably fun for about 2 minutes because you're like, oh my gosh, I'm running, I'm feeling fit. I'm like that girl in the movie that has the perfect ponytail. But then after about 2 minutes, your body starts panicking because this is a new experience and the body does not like change. Um, yeah, the mind doesn't like change. The body is not going to like change. Your body gets a little bit stressed out. Your blood pressure increases, your heart rate increases. You start really, really sweating. And after a while, you are not the cute girl with the ponytail anymore. You are the raging hippo that's like dying and melting at the same time. But after about 3 years of doing the same thing, it's a little bit different. When you go out for that 4 mile, let's just say you started running 4 miles. I didn't do that when I first started running. It was a solid 10 minutes of death. But say the first time you run 4 miles, you feel that like terror and despair and pain. After about 3 years of doing that, instead of feeling like that insane jump in blood pressure and heart rate, you kind of get a little rise and stuff. You know, you're out here moving and you can actually see the trees. You might even be able to talk with a friend. And that's like the chronic adaptations. Day 1 is acute, year 3 is chronic. So even though we talked about basically, we just finished talking about the vibes and how you feel, but we need to know what's actually going on in your body. There are a lot of words on this slide. And I'm going to try my best again not to read word for word. But we're going to first talk about cardiovascular responses to endurance training. So obviously, your heart gets excited and there's an increase in blood flow. I don't know, are you guys pretty familiar with the sympathetic and parasympathetic nervous systems? So they're both working at all times. None of them just shuts down magically because the other one is running. What is the parasympathetic nervous system responsible for? Yes. And what about the sympathetic nervous system? Yes. And so when you exercise in that one training in that one training session, that sympathetic nervous system takes control. You still, like I said, the parasympathetic system is not a computer that shuts off. The sympathetic nervous system acts, like she said, as a flight or fight response. Your heart rate's going to increase because your heart is stimulated by that system. Once that takes place, you're going to experience an increase in cardiac output. Does anybody know what cardiac output is? No? Never heard of it? What's up, Luke? Yes, per minute, actually. Your stroke volume is the amount of blood you pump out per heartbeat, and then your heart rate is the amount of heartbeats per minute. Your cardiac output increases because your heart rate is going to increase. When you first start that run, and I keep going back to running because I love running. There's probably other examples out there, but you go with what you know. But when you first start running, there in no way is your heart rate just going to stay at that average 70 beats per minute. It has to rise to the occasion because you're doing a lot more. So again, first start running, your heart rate is going to jump up to around 120 to 150 beats per minute. That means you're experiencing, again, a lot of beats per minute, which increases cardiac output. Your stroke volume is the amount of blood pumped per heartbeat. This happens because you got to get all that blood not much quicker. That's related to heart rate. You got to get a lot more blood to your body. And it doesn't mean that your blood volume increases. It means for each pump of your heart, there's a lot more blood coming out. And we'll explain more of that later. There is a decrease in total peripheral resistance due to vasodilation. And so what that means is, and I couldn't find a picture online because the thing about like pictures on PowerPoints is you have to cite it. And I wasn't feeling like I wanted to like cite things to make sure everything's accurate. So yes, I do have a ghetto picture of a big man with a heart. It's probably not accurate, but I thought I'd draw a little bit an artery. So your arteries, on a normal day, kind of like this. This is a terrible draw, but I saw the draw kind of like this. So your blood flow is really not requiring much, like the widening and the shortening. You're not really under stress. You're just chilling. You're chilling in class. Now, when exercise starts, that decrease in total peripheral resistance, because your arteries take a certain shape. Your muscles stimulate that. It's just going to keep itself together. Now, when exercise happens, this is going to widen so that more blood can flow. So your heart rate's already increasing. Your arteries are widening so that each heartbeat, more blood can flow, and this is the tissue. I promise this is going to make a lot more sense here in about 15 minutes. You will also experience a very obvious change in blood pressure. Not so much in diastolic blood pressure, but more so in systolic blood pressure. Systolic blood pressure is going to increase in direct proportion to the intensity of your exercise and that cardiac output. I'm saying this like you guys knew me yesterday, but back in South Georgia, I worked in an exercise medicine clinic for older people. We had people from all backgrounds with all sorts of diseases. We had the super healthy old guy who golfs every Monday, and then we had the guy with chronic heart failure who really needed to stay fit so he didn't absolutely die. We had a couple of people that were there that took beta blockers. Do you guys know what beta blockers do to the body? They keep that blood pressure fairly low. People with high blood pressure tend to have a lot of damage to the heart because you have a lot of blood pressure, or not blood pressure, you have a higher blood pressure at rest. And over time, when you have that high stress on the body at rest, things break down quicker. It comes in an inappropriate setting. So when somebody comes into this clinic on beta blockers, their blood pressure is forced to stay at that like maybe 120/80, 140/90. So when they start working harder, you're not going to see that linear increase in systolic blood pressure. So to make sure nobody like fell apart or died, my job was to keep an eye on them when they exercised. It was very boring, but it was very important. We didn't want them to go crazy on the exercise and not experience and not get that increase in blood pressure that they needed to get more blood to the tissues. Does that make sense? Okay. So I've been yapping for about 10 minutes. Are there any questions? No? Are you sure? This is about to be another like 15-minute session of me yapping. All right. So we're almost wrapped up with cardiovascular responses, and then we're going to dive into respiratory responses. Another thing that happens to blood itself is that there is a decrease in plasma volume. What is plasma? What is the blood plasma? How about you? How about you know? Well, this is why you're in class, so that you can know. The plasma is the fluid part of the blood. And with that being said, now that we've defined it, why do you think there's a decrease in plasma volume while you're exercising? You could just take wild guesses. You in the back. Yes, absolutely. You hit it on the head. There's fluid distribution in the body, and then there's fluid distribution that results in sweating. And you can think of it like quite simply that you can picture that with this decrease in plasma volume or with this sweating and stuff like that, your blood technically gets a little thicker. In response to this, this is the reason why we have to hydrate. So when you're losing a lot of this fluid through sweating, you still have a very great reserve in preparation for that. This increase in hematocrit is an increase in the ratio of blood cells to the total blood volume. There's no actual change in the number of red blood cells. It's just when something decreases, there's more of a presence of something else. There's also, and we talked about this with the little terrible diagram of the artery, there is a dilation of coronary vasculature. Simply your arteries that support your heart also widen. So more blood can get to the heart itself. Because I'm pretty sure you guys kind of have an idea of the fact that like your heart also needs fuel as well. So there's arteries and veins there that need fuel too. So those arteries widen so your heart can do more of its job. Moving on to respiratory responses. Sorry. Moving on to respiratory responses, there is an increase in real time of pulmonary minute ventilation. Does anybody have an idea of what pulmonary minute ventilation is? It's okay. Sorry, I'm asking a lot of questions. I just like little pauses because sometimes I get nervous and I'm like, oh, let's just ask a question. And that gives me an excuse to reset. So you don't necessarily have to answer it. It just gives me time to be like, okay, I'm still teaching. Let's focus. So pulmonary minute ventilation, you can kind of compare it to cardiac output. Like we said before, cardiac output is the amount of blood that's pumped out of the heart with each heartbeat per minute. Yeah, I think I said that right. Pulmonary minute ventilation is the amount of air that blows through the lungs each minute. This is a product of breathing rate and tidal volume. So tidal volume is that amount. Let me double check my notes. Hold up. Okay, increase breathing. Okay, tidal volume is the amount of air per breath, and breathing rate is the breath itself. Does that make sense? So just remember, cardiac output is similar to pulmonary minute ventilation. This pulmonary minute ventilation increases because you need more oxygen. Your body's pulling in more oxygen, so the blood can be oxygenated and then eventually get to the tissues. You're not gonna like your body's not going to roll with the same amount of oxygen it's extracting with you sitting there and me standing up here. It needs more because you're doing a lot more. Another thing that increases is the respiratory exchange ratio. Have you guys heard of RER? Just shake your head or nod your head. Okay, simply, this is the ratio of your carbon dioxide, the carbon dioxide that your body produces over the amount of oxygen your body consumes. So I'm going to try my best to go back to this chalkboard to make it make sense. So I don't completely read off the slide. So we're going to take it back to oxygen. Your body pulls in that oxygen to hit the blood. The blood flows through the body. We're just going to use the skeletal muscle as the point of contact. That blood is the skeletal muscle tissue. And again, keep in mind that this blood is carrying that oxygen, so the oxygen is going to it. In times of stress, like this run, and eventually I got to label this run as like a 30-minute, like picture your dad telling you that you're to exercise. You're that nerd that loves air conditioning and math. So he's like, get outside, go run. We're doing this. So Padre says, 30-minute run. You don't know what you're doing, so you go out hard. Because you're going out hard, your body's pulling in more oxygen. Your blood pressure is going higher, so blood can hit the skeletal muscle faster than it was before. So that oxygen reaches the skeletal muscle. Thank God. your oxygen gets dropped off here. And there's like a million, I'm gonna say 1,000 because I don't want to write more zeros. There's like a million things that happen here, but that's another class, and I only have like 34 minutes left. So skeletal muscle gets that oxygen, and then a response to this is carbon dioxide production. Carbon dioxide technically is like the waste that your body produces in response to what you give it. So your body's not just pulling in oxygen and just becoming better. There has to be something has to be given back. So carbon dioxide is made. So RER, that's not it. RER is that carbon dioxide you produce. Also, where does that carbon dioxide go once it's made in the tissues? To just hang around there? You exhale it. So this is going back out. So in, out. So carbon dioxide out, and then the oxygen you produce in. The harder you're exercising, the more carbon dioxide you're going to produce. And eventually that's going to outpace the oxygen that you consume. So this doesn't mean death. This is just representative of the stress and suffering that you're enduring during this very, very difficult run. So RER not only does it reflect the oxygen you're taking in and the carbon dioxide you're producing, furthermore, it measures the proportion of fat, carbohydrate, and protein used during aerobic processes. Protein, this is just a PSA, protein is not necessarily used during aerobic exercise. That's used for like recovery and muscle building after the fact. Now, if you are an ultra marathoner, you've been out there in the woods for forever, and you've burned pretty much all your carb stores and your fat stores that you possibly could in the body, your protein, you start burning protein. This protein comes from your skeletal muscle, unfortunately. I'm sorry. Unfortunately, and that's just a sign of muscle wasting, because if you didn't use your protein, you would die. Pretty morbid, but that's the case. Fat is oxidized, or fat is burned when there's a lot of oxygen provided to the body. Carbohydrate is also burned in that situation, but it can be burned using anaerobic means as well. What does anaerobic mean, guys? Well, that one? Absolutely. We'll go with that. Thank you very much. So fat, 100% air or oxygen, and carbon dioxide can take different, can take oxygen or otherwise. Back to the board. So fat in, through, out, it's perfect. Your carbon dioxide production is going to be significantly less than your O2 consumption. Sometimes, like the harder you go, like I said before, the higher this ratio, just because more carbon dioxide is produced at the same oxidative experience. Have you guys heard of glycolysis? Okay, yeah. So glycolysis can take two routes after you've broken down the electron transporters, like gotten like those 2 to 4 ATP. You can either make lactate or pyruvate. As you know from biochemistry or something like that, pyruvate goes into the Krebs cycle or the TCA cycle. You make thousands of more ATP cells. That lactate I'm not going to say kind of stays where it is. We're just going to call it staying where it is because, again, that's for another class to get a step further. Once you start producing that lactate, that is also reflective of the fact that you're using more CO2 because you didn't throw it into that oxidative pathway. It's going to form an anaerobic pathway. Does that make sense? Clear. Okay, you don't necessarily have to write that one down. I don't think that's going to be on the test. Cool. And as you can tell, a lot of this is related to energy. We need energy in these situations, and we need it right now. ATP is absolutely needed. ATP is the energy currency of the cell. I'm sure you've heard of this, and eventually, are you guys like freshman, sophomore, junior? You have a freshman? Okay, you have about 3 more years of hearing the word ATP. Your metabolism increases to make more ATP. And briefly, can somebody define metabolism? It doesn't have to be like the super scientific description. Yes, it is actually the sum of all those processes that take place in the body. So, like I said before, your carbon dioxide increases because more oxygen is being used. Your lactate production increases because more carbs are being used for the creation of energy fast. Fast energy is created anaerobically, and the byproduct of this is lactate. Something else that increases is your body temperature because a faster metabolism is reflected of more heat creation. A lot of heat is created during these like biochemical processes. So increased heat production also suggestive of the fact that you are going to sweat more because your body eventually has to get rid of all that heat so you don't cook. All right, now we're going to dive into some hormonal responses. I don't have as much experience in endocrine responses, but we're still gonna like tackle this together. So during acute exercise, you have an increase in glucagon secretion and an increase in insulin secretion. The hormone glucagon, sorry, the hormone glucagon is there to stimulate the release of carbohydrate or sugar into the blood. Insulin does the thing where it takes that blood sugar or that glucose and takes it into the tissue. So when you're exercising, you need more sugar to make more ATP. And sugar, I'm going to use sugar and glucose interchangeably. But yeah, you need more of that to make more energy. It doesn't really make sense for your body to activate that insulin response to take in more when you actually need it out there. Something else, let me double check that I like. Okay, yeah, so we hit that on the head. There is a decrease in cortisol with low intensity exercise and an increase with moderate to high intensity exercise. Let me check my notes to remember. Okay. Cortisol is used for glucose production or glucose oxidation. When you're doing a low intensity exercise, like that nice walk you're going to take with your friend later on today to like relieve stress, you're not going to need as much cortisol because you're burning more fat. That is used at rest or during low intensity exercise. At moderate to high intensity exercise, you're going to need more carbohydrate, glucose, or sugar action. We're going to use those interchangeably, like I said. Cortisol has a lot to do with stress. So that sympathetic nervous system interaction plus the cortisol is really what plays a role here. There's also an increase in growth hormone, specifically during prolonged exercise. Growth hormone specifically mobilizes fat stores for prolonged exercise and can aid in recovery. So prolonged exercise, again, I'm going to refer to ultramarathons. You're going to burn a lot more fat. You need a hormone to back that up. Now, catecholamines, epinephrine, and norepinephrine are increased because, like the young lady with the blue shirt said, something has to happen with that flight or flight response. And these are the hormones responsible for that. That being said, any questions, reflections? No? I know Dr. Gaines likes examples, and I'm trying to find a good example to wrap all of this metabolic and endocrine responses up. Let's see. Say that one more time. Growth hormone is used to stimulate fat oxidation. You pretty much only need fats at low intensity exercise, like walking, very slow running, and even at rest. So you guys are burning primarily fats this time. So growth hormone is probably actually running just to make sure that fat oxidation is stimulated. Any other questions? Do we need to back up? No? Let's see what's on this next slide. So we've dived into acute responses. Now we're going to slide into chronic adaptations. So eventually, we said before, the first instance of like that 1 30-minute run is going to be terrifying, very painful because your body's adjusting on the fly and has to like respond accordingly. Eventually, your body realizes that you're not going to stop doing this. So once after that first run, your body's going to assume like, okay, cool, this is never happening again. That's really traumatic, but like we're good. It goes back to like homeostasis. And then the next day, boom, 30-minute run because your dad said, listen, go back outside. You're sucking up all my air. Quite literally, I think that's what my mom and dad said. They were like, get outside. I sucked at all other sports. So I was like, I gave up, did academics. And they were like, absolutely not. So I go back outside for my 30-minute run. It's still a little bit traumatic, but my body's like, okay, we've seen this before, so we're not going to completely fall apart. And then 2 months later, eventually, I mean, not eventually, 2 months later, I was still out there doing the 30-minute run. Eventually got bored and was like, okay, we're going to make this a 35-minute run. About a year later, I was like, let me see if I could be like my teammates because I joined a cross-country team. Do like that 50-minute run because coach said if I ran 50 minutes, I would get faster. And so on and so forth. Like 15 years later, now I'm like running every day and it's great. Anyways, so your body gets used to the fact that you're going to be doing this. You're going to be doing this for a long time. So it makes adaptations to survive this. Can somebody define VO2 max for me? You guys have seen the test. It's super hard. But what are we measuring? Yes, at the highest point. It's the maximum amount of oxygen your body can take in. So great job. This increases over time because you get a higher maximum cardiac output and higher oxygen extraction. So that the first adaptation your body does is it improves its ability to take oxygen from the blood and use it at the tissues. The first time it's not going to do the whole thing right. It's going to take some of it, still feel traumatized. The more you do it, the more it's going to be like, oh, this is how I take up the oxygen. This is how I'm going to do it better. And after about a year, it's going to be pretty much a pro at it. You're going to get a higher maximum cardiac output because literally your heart's going to get stronger. Your left ventricle is going to increase in size. Your heart muscle is going to get thicker, which is really, really cool. And then once that blood, and this is for another class, but like eventually your blood comes back to your heart, rebounds, and then gets shot back out to the rest of the body. So when that blood hits the heart, or hits the atrium, hits the ventricle, it kind of does this rebound thing where your body it's kind of like a rubber band. Like your left ventricle kind of like bounces back and then shoots the blood everywhere. Over time, this becomes like a lot stronger. So instead of just doing this like it did the first time, after about a year, it does this and shoots the blood out. So it goes faster and you can get that oxygen to your tissue faster. And even cooler, once that oxygen hits the tissue, it pulls it out better. Does that make sense? Okay, just remember the rubber band thing. Another cool, interesting thing that happens within just 2 to 10 weeks is your heart rate drops at the same intensity. So picture this run. I'm going to see if I can draw the table. I was looking at this like 20 minutes before this started. The graph. Here we go. The graph. So this is going to be make up 100 beats per minute, 150 beats per minute, then 200 beats per minute. And this is going to be like speed. So say that first run, the speed was like 5 miles an hour. At 5 miles an hour, that first run, your heart rate was definitely maybe like 150 beats per minute. I'm just going to draw this line. So when I draw the next one, you'll see the change. After about 2 to 10 weeks, instead of your heart rate being like 150 beats per minute at that 5 miles an hour, it's not going to go all the way down to 0, because if it did, you'd be a superhero. It's going to decrease maybe down to like 140. So at that same speed, okay, let me see if I can draw this right. Okay. The same speed, heart rate is there. And eventually, over time, that heart rate is going to get lower. So where you're going to be such a pro athlete or a pro cross-country runner that when you go out and run 5 miles an hour, your heart rate is going to be like a solid 120. Does that make sense? So your heart rate max, unfortunately, does not get higher. Unfortunately, the older you get, your heart rate max is going to get lower. I don't know if you guys have seen the 220 minus age, equation. So the older you get, the slightly lower that's going to be. When I was like 20 and stuff, I was like, haha, max heart rate is 200. Now I'm like 25 and it's like 195. And you think it doesn't matter. That's like a 5 beat per minute difference. but it does. So when you compare yourself to 20-year-olds, when you're 25, you're gonna be like, bro, like it seems like you can't do as much. But I digress. Your stroke volume, and I think I brought this up before, is going to increase because, like I said, your left ventricle size is going to increase. Cardiac output, again, is the amount of blood pumped out of the heart with each heartbeat. So we were talking about like that stretch response. When the left ventricle gets stronger, this rebound effect gets a little bit stronger, and so you can push out blood more or push out more blood. And again, your myocardial wall thickness gets more like your myocardial wall gets thicker because basically you're building heart muscle. We go to the gym to build like skeletal muscle, and it's very obvious when that happens. But we forget that your heart can increase. You probably heard like your endurance runner friend, or if you're that friend, probably heard that them say stuff like, "Oh, my heart is enlarged," so like, or basically like a superhero or whatever. You probably never heard the superhero part, but like endurance athletes have enlarged hearts simply because of this. Just like weightlifters usually have larger muscles because they lift a lot. You're also going to have an increase in red blood cell volume. Your body, like after doing this for a while, is going to realize, like, okay, I can't really do much with the amount of red blood cells I have now. She's obvious, he or she is obviously going to be doing this for a while, and they're probably going to do more. So in response to this, it gets more red blood cells. And it's not like that thing where you like go to the store and just get more like food. No, it's this thing goes to the bone. It's actually within the bone marrow that red blood cells are created. And this is simply called an increase in erythropoiesis. And I probably said that wrong. I don't use that word a lot. And erythropoiesis is the act of like creating more red blood cells. There's also, we don't really talk about blood pressure that much because it really doesn't change that much in response to like chronic exercise. This actually changes probably less than 10 millimeters of mercury. But what does change as well is the increased capillary density of peripheral skeletal muscle. So arteries are a lot bigger than capillaries, but like I said, like I was explaining, and this is actually before when we had the RER diagram of like in, out, through, we're going to take it a little bit deeper. So this is the blood. I'm going to like label it just so you guys don't forget that these two lines are like the artery, which has blood. And by the way, in the blood, there's some oxygen hitting it. And this square finally represents the tissue, a piece of skeletal muscle. So O2 hits it through the blood, bam, it becomes oxygenated. Like, remember me saying that there's like a million different steps between this and being oxygenated? This is one of the million steps. There are a bunch of capillaries. These are like very tiny arteries that are the routes that oxygen takes to hit the tissues. So over time, over that year, your body's going to make more capillaries so you can get even more oxygen quicker. What's that? Oh, and this is directly related to that increased oxygen extraction. You can extract or take in more oxygen because your capillary density increases in your peripheral skeletal muscle. And peripheral skeletal muscle, this is like skeletal muscle in your periphery. So yeah, very bad diagram, but these little lines are just capillaries, and you get more of them the more you do something. So blood can hit, like more oxygen can hit the tissue because you have more routes in the tissue. Just hilarious. Like adding more highways to get to the same place, or adding more lanes on a highway so that more things can get to the same destination. It's like construction on like, what is that highway? 81? Yeah, they're like adding an extra lane. It's the same thing. All right. I think. Blah, blah, blah. Okay, next slide is a question slide. Any questions? I did a lot of rambling. Probably was a little bit confusing. Anything? So you guys basically understood everything that just happened. Dope. Onward. So when talking about respiratory adapts, respiratory adaptations, these are not really a limiting factor for performing max exercise. So not a whole lot of changes occur. But at submax exercise, that pulmonary, minute, or minute ventilation decreases. Again, you can think of pulmonary minute ventilation as cardiac output, similar to cardiac output, but something's actually decreasing in the situation. So you have an increased tidal volume. So that's the amount of air you take in with each breath. You have an increased tidal volume, tidal volume, because your body's becoming a pro at like breathing more or breathing better, like taking in more with each breath. So instead of like that shallow thing you did that first one where it's like, because you're hyperventilating, your body's shocked and terrified and betrayed, that you do that little hyperventilation thing. Over time, your body calms down, and instead of doing this, going up Chicken Hill, your body's doing more of like a, you just got that like demonstration for me for free. You ever like check yourself out and you realize exactly what you're doing in front of people? It was like not me like keeping it hoeing in front of these kids. Sorry. But anyways, higher tidal volume, but you have a lower breathing frequency. Why do you guys think this is the case? You're breathing less, but somehow you're still exercising. Like what, like, this is a weird phenomenon. Picture yourself doing the same thing. It's like we had the 1 30-minute run at 5 miles an hour, but we're doing the same run maybe 6 months down the road, 5 miles an hour, 30 minutes. Why would your breathing frequency decrease between run one and the run 6 months later? It's because you're not working as hard. Yeah, it's just less effort. And you're better at taking in more oxygen per breath. Why use more breaths when you can use less? You're getting the same thing. As far as maximal exercise, your pulmonary minute ventilation increases. And this is basically because you're breathing more, because it's really, really difficult. So at this point, you're a pro at taking in more air with each breath. So each breath gets more oxygen, each breath gets more air, and that leads to that higher pulmonary minute ventilation. You also become more efficient. And this is a little bit difficult to explain because I just saw this sentence like 2 days ago. It usually takes me about like a week or so to like get ready for like a lecture, but it's fine. So you have a decreased energy cost to each breath. It's easier to take the breath. And this allows for more oxygen use by the skeletal muscle. So it's really cool that what happens here affects what happens in your muscle. Your diaphragm is a muscle, which is crazy. So the stronger that is, the easier it is to the slower it takes to get it fatigued. I found this picture on Bing.com, so I didn't have to cite it. This is a cross-sectional view of some random skeletal muscle, but I promise it's a skeletal muscle. Some intramuscular triglycerides there. Surprise, surprise, your skeletal muscle stores a couple things like fats, and there's some glucose and stuff stored in here. I think you guys already knew that because obviously insulin is the thing that stimulates your muscles to take in more glucose. So there's really no change in the cross-sectional area of type 1 fibers. Should also note that type 1 fibers are the ones that help provide that oxygen, or like are the ones that where that oxygen extraction and stuff take place. There are small changes in fiber type distribution. So you have a decrease in type 2X fibers, and these are the glycolytic fibers that use a lot less oxygen. Like they can use oxygen, but it's not like primary. And then there's an increase type 1 fiber. This is directly related to performance. So another example, again, like I said, I'm a runner. I'm probably not going to use another example. I don't really know, like I've done elliptical, but I'm not going to use this as an example. Again, when you're teaching yourself, you just use what you know. Don't like try to change up the game. So when I say this is in direct relation to performance, me running in 6th grade, that 30-minute, 5-mile-an-hour run, it gets better and faster over time. So that was 6th grade. In 10th grade, I could do that 30-minute run at like 8 miles per hour. And this is because my capillary density increased. That terrible, where's my chalk? Okay. This terrible diagram is exactly reflective of what happened over those, like, let's say 10th grade, over those 4 years. I had more capillaries to get more, more opportunities to get blood to that tissue that needs it, which means more opportunity to get oxygen into those tissues and get more efficient. I also had an increase in mitochondrial density and mitochondrial size. I know social media like 3 years ago was like mitochondria is the powerhouse of the cell. That's because your mitochondria are where that ATP production takes place in an aerobic setting. When you have more of that, when I had more of that, I had a better I'm going to use the word opportunity because that's the only word that's popping up in my head. I had more of an opportunity to get more ATP created. My mitochondria also got bigger. So if you have bigger nutrient factories, if I have bigger like car factories, I can make more cars. So if this is a smaller plant, working only able to make like 3 cars a day. This is a terrible example, but it's all I got. So work with you. However, when we expand, because we got more money or we did more training, pushing out 5 cars a day. Okay, to make sure I do 5. Then eventually we get even a bigger plant. We're able to make like 10 cars a day. We're basically like Nissan. It's very similar when it comes to mitochondrial size. Bigger plants and also more plants. There's also an increased activity of oxidative enzymes, and that is 100% biochemistry. So we're just gonna I'm just gonna say that and we're gonna move on. However, if you want to talk about that in more detail, see me after class because it's a beautiful, beautiful thing. You also have increased intramuscular glycogen stores and increased myoglobin stores. This is really cool. I didn't learn this until I was like in my master's. You actually have oxygen already stored in your muscle. There's just not a whole lot of it. But over time, you get more. And I'm not talking about you go from like one little molecule of oxygen when you first start exercising, and then you get like a trillion. That's not the case. It's just like maybe one molecule, like you get like 15 more. It's like you get more of a reserve. It's like going from a car that when you hit E, you surprise have like 10 miles left before you can get to the gas station. You have a better car which gets 50 miles once you hit E. Does that make sense? You guys all know like once your car hits like empty, you still secretly have like a couple more miles left. Yeah, it's getting a better car with like more emergency miles in it. Again, I think that's a good example. You guys let me know, hit me on my email and be like, you could have, this is the example you could use because I'm probably going to teach this again somewhere. See where we're at. So this is kind of sort of the end of the lecture. I titled this Subtly Putting Things Together. The main thing is you have a lot of metabolic adaptations in response to acute exercise and chronic exercise. And this is the result of changes in 3 different systems: the cardiovascular, respiratory, and skeletal muscle systems. And I don't want to lie to you, let me backtrack. Major changes take place in these 3 systems. You have a lot of other things changing, like your nervous system and all that cool stuff. We just didn't dive into that today. Over time, you're going to have an increased reliance on fat as energy because you're doing stuff at a lower effort. And again, you need to remember that at lower efforts, you're burning more fat. You have a higher lactate threshold, which means I always forget lactate threshold. Give me just a second. Okay. Simple definition is that lactate threshold is the point at which you're making more energy from an anaerobic standpoint. So below lactate threshold, everything's pretty much organically like aerobic, oxidative. But once you hit that lactate threshold, that's when things get harder, and that like change gets a little bit more nonlinear. Your VO2 max also will increase by about 10 to 30% because of all those other changes I just talked about over the past 9 slides. And all of this leads to a greater capacity to perform at higher exercise intensities for longer periods of time. And yeah, that is the end of part 1. Like I said, I recorded this. There are probably a lot of ums and hums and pauses, but I will send this to Dr. Gaines. And if you guys want to listen to this again at 2 times speed, yeah, feel free. Are there any pressing questions? Is there anything that you think I like missed that you need to like get a better understanding of, or something that I need to re-say? No? Okay, cool. Well, it was great to hang out with you guys. Thanks for listening. I guess you're free to go.